This result okay, so we're going to take g to be the low degree part of the function. So it's the sums of f at s chi s over all small sets s. And then we can basically want to upper bound the L2 norm of G. So this is the sum of S mostly of f at s squared. But the L2 norm of G is also equal to the inner product between G and F. And what we said earlier is that F has this behavior, this kind of distribution, and G has this kind of distribution. And we're going to use that to upper bound to say that G and F are not correlated. So this is by application of Hausdorff inequalities. We can say that this is at most the form of G times the third norm of F. And now we can say that this is at most. So now it's going to be 3 d over 2 times the 2 norm of G. And since f is Boolean, it only takes the value 1 and 0, we can say exactly what this thing here. This is epsilon 3 over 4. Okay, but now we are actually done. So we can rearrange and take squares. So rearranging we get the norm of G is at most 3 to the d over 2 times epsilon to the 4. So we can take squares and finish it. And here the first inequality is for a mislemma. This is because f takes value 1 and 0, so we have this. And this is a Hausdorff inequality. Now let's prove this one. Okay, so Friedwood statement is over there. It says that if the total influence is small, then F is fully concentrated on a very small set of Fourier coefficients. And what we're going to do is to define this set J, consists of all I, such that the influence of dice influence of F is at least tau. And tau, we're going to choose it to be epsilon squared 9 to the minus of the influence of F over epsilon. So we're going to choose some small parameter tau. Maybe I should recall the notion of influence. So the ice influence of F is the probability that if you flip the ice coordinate, it changes the value of F, and it's equal to the sum over F containing I over F of S squared. So we take the set of coordinates with large influence, and we are going to define the set F of notable Fourier coefficients, a small set of notable Fourier coefficients, to be the set of all F's, such that the size of F is at most the total influence of F over epsilon, and S is contained in J. Basically, a set is notable if it's contained in J, and we already know that we can discard all the large sets if the total influence is small, so basically we keep all the sets that are small, that are contained in J, and add small size. What we're going to show is that our function is fully concentrated on this family F. I suggest what can we say about the size of J? This is at most the total influence over tau, because the sum of the influences is at most the total influence, but each one of those influences is at least tau, and this is going to be e to the O by F over epsilon. And this implies that the size of F is at most J to the IF over epsilon. And this is E to the O of I squared over epsilon squared. So the goal will be to show that the Fourier spectrum of F is concentrated inside this family, and then we'll be done. Okay, so now we want to upper bound the sum over S not in F over F at S squared. We can say that this is at most epsilon plus the sum over S such that S is not contained in J and the size of S is smaller than the total influence of F over epsilon. Because we already know that the sum of Fourier coefficients that correspond to set of size at least total influence over epsilon, this contributes at most epsilon. So we only need to upper bound the sets that are not in F and also have small size. Okay. And now what we're going to do is to say that this is at most epsilon plus the sum over I not in J, sum over the sets S that contain I and are small over F at S squared. Now we have this LIF that was the sum over S that contains I of F at S chi F. So now this function is a function that takes the value of -1, 0, and 1. And for I not in J, this function has small expectation. It has expectation smaller than tau. So you can apply this theorem by KKL.
But this function, absolute value of this function.
Yeah, absolutely. Okay. Yeah, I should have. So, okay. Yeah, probably should just modify it to include functions into -1, 0, 1. And the same for forks. And here put the expectation of absolute value of epsilon, and then same thing works. Okay, so we have. Okay, so here we have the sum over I not in J, sum over S containing I and S small of f at s squared, we can write it as the sum over I not in J, the sum over S of LAS hat S squared, where the sum here is over small n, small sets. Okay. So now we can apply KKL, this version of KKL, to say that this sum is small. So this is at most direct influence to the power 1.5 times 3 to the d. And this is at most the sum over I not in J of tau to the 1/2 times direct influence times 3 to the d, which is at most the total influence of F times tau 3 to the d, which is at most epsilon by the choice of tau. So that completes the proof. But the idea was basically that you have those Li those Laplacians, and these corresponds to sparse functions. They take values, non-zero values, on a very small set. And then KKL tells you that they are concentrated on the high degrees. The full spectrum of these functions is concentrated on the high degrees. But overall, the full spectrum of the function is concentrated on the low degrees. And this tells you that all the notable Fourier coefficients lie in this small set of sets S that are contained in J. And this theorem tells you something stronger, that your function...
So maybe it's good to write that you use G and influence of F divided by epsilon interchanging this. So G is influence of F divided by epsilon, right? So what is G? It is exactly influence of F.
Yeah, right. That's, yeah. Mm-hmm. Yeah, so basically let's go back. So we wanted to, we had, so what wanted to show that the Fourier coefficients that corresponds to small sets. Yeah, so we got rid of the large sets just by using the trivial bound. And then we only cared about the small sets and wanted to show that the small sets, they must be contained in the set of influential variables, basically. So I want to say that we can basically discard from every set that contains a non-influential variable is already not knowable. And the reason is basically that if S contains a non-influential variable, then it's also a Fourier coefficient of these Laplacians. And these Laplacians have all the full spectrum concentrated on the high degrees. So together you get pretty good. So are there any questions?
But if you just want to approximate by a junta, then somehow this is not very efficient, right? Or
this is what you get for junta. Yeah.
you get your junta, but you get something like that 2 to the influence, maybe.
right?
No, what? You get, no, the size of J is exponential in I over
Okay, I
epsilon.
just want to see if you don't do anything, then you get this 2 to the third.
Yeah, but if you just want to apply Friedrich-Grunde theorem in the black box, yeah, then you get that. But actually, you can discard all the large Fourier coefficients. So you get this. Yeah. If a Friedrich-Grunde theorem tells you that you're close to a function that depends on this set J of coordinates, which is what we showed. Do you have any question? Okay, so talk now a little bit about the noise operator.
So we just find variables where influence is sufficiently large, and everything is concentrated basically on S, which have
Exactly.
sectors.
Because the large sets we don't care about, and if you are a Fourier coefficient of LIF or I is a small influence, we also don't care about it, and then the remaining ones are those sets that are contained in the set of influential variables. And Bonamy's lemma is proved with the help of the noise operator. And the theorem called, okay, one way to prove it is by proving hypercontractivity. And then I have to define the noise operator. Suppose that you have X in the cube. You can define a distribution and delta of X. So this is a distribution on the cube. Where we choose Y in that's correlated to X. So the probability that Yi is equal to Xi is 1 plus delta over 2, independently for I. So if delta is 1, you choose Y to be equal to X. If delta is minus 1, then Y is the opposite of X, and otherwise, and if delta is 0, Y is independent of X, and in between, if delta is positive, then Y is correlated with X. And then the noise operator in delta f of X is given by the expectation over Y of f of Y. Okay, so this is the probabilistic definition of the noise operator, but it has a nice Fourier interpretation. It turns out that T delta over F is the sum over S of delta to the S f at S chi S. So this is a smoothing operator, and it essentially kills the high degree. And the hypercontractivity theorem I guess it's due to Beckner, and you can deduce Bonami's lemma from it. The paper was earlier, and it was in French. Result was independent. So it says that if delta is at most square root, so it is at most q, and more than 1, and delta is at most square root of t minus 1 over q minus 1. Then t delta f and q is at most ft for every function.
Is that related to this sharp Young convolution equality? This hypercontractivity?
Sure, but maybe, I don't know.
I think this Hausdorff paper,
Sharp Hausdorffian.
What is the question?
It's related to sharp Hausdorffian.
Whether it's sharp?
no, whether this is related to sharp Hausdorffian.
Ah, yeah.
Okay,
Yes.
This is Hausdorffian, not the convolution.
And then, as a corollary, you can deduce a result that's stronger than what we described earlier as Bonami's lemma, that suppose that f is a degree d, and then fq is at most square root q minus 1 f2 all q at least 2. Thank you. Yeah. And the proof is that you let set delta to be 1 over the square root q minus 1, And then you can define this function g to be the sum over delta to the minus f of s by f. And then the delta of g this is just equal to the delta of g is just f. And then this is at most g2 by hypercontractivity. But this is at most delta to the minus d and 2 normal f. Just by possible. Okay, and then if you use the power that you get from this Q and not just choose Q to be 4, you can prove a stronger level D inequality. Suppose that you have a function f to 0, 1. With expectation epsilon. And suppose that D is smaller than log 1 over epsilon. By optimizing the parameters, you can show that if you sum all the Fourier coefficients at level D, you get that this is at most epsilon squared up to logarithmic factors.
One squares of your coefficients.
Right.
Thank you. Okay, and you add constant. So earlier we had epsilon to the 1.5, and you can actually get be very close to epsilon squared and get only logarithmic factors. And the proof is very similar to KPL. You just do you let G be the sum of small Fourier coefficients. And then you say that the correlation between F and G is smaller than GQ and FQ prime. And this is at most Q minus 1 d over 2 G2. And here this is epsilon to the power 1 minus 1 over Q. And you rearrange and choose parameters optimally, you get this inequality.
And if D is larger than log 1 over epsilon, then you don't expect to have any bound that goes to 0? Or?
So, yeah, so there, yeah, I don't expect to get little of that. We have examples, yeah.
Now, did you finish the proof? Or?
Yeah, so this, yeah, basically, now we do the same as KKL, you rearrange this G2 to the other side.
But you need to choose Q correctly, right?
Yeah. So I don't see a point in doing this, but yeah. It's an exercise to finish the proof. You choose the Q to be log 1 over epsilon over D. Times 2. Okay, cool. So now I'd like to tell you about things that are more recent. But maybe before I switch to another topic, maybe there are questions.
Yeah, maybe you said this, but do you use Beckner's hyperconjectivity to prove Bonami's lemma?
Yeah, so this is this thing. Yes, you have hypercontractivity, then you easily can deduce Bonami's lemma. Bonami's proof, I think, was using hypercontractivity. Yeah. And if you choose the parameters in a better way, you can get this level D inequality. Q to KKL essentially.
So we should think about that as sort of something better than KKL, which you cited before.
Think about this. Yeah, better than the KKL cited before because like if you normalize F to have expectation 1, then the epsilon square vanishes. And it's a very significant improvement. It's from polynomial in epsilon to something logarithmic. And we'll actually use this fact soon. So you get a exponential improvement in other results. And yeah, even the case D equal to 1 is sort of interesting. You can deduce Chernov's inequality. It's essentially equivalent to Chernov's inequality. The case where D is equal to 1.
Can Q be P, like P and Q?
P equal to Q?
Yeah.
Then OS becomes 1.
So what becomes?
I mean, if Q is equal to P, then this operator is a contraction in LP because it's an operator corresponding to a random walk. It's a contraction in LP. So.
Okay.
So any more questions? No? Okay, so I want to tell you a little bit about how hypercontractivity about applications to group theory. and also to representation theory. But I'm not going to assume that we have backed up to this topic. So suppose that you have a group. A subset of G is said to be product free. If all A in A and the product AB is not A. So this is sort of the opposite of being a subgroup. It means that for each dimension in the set, the product is not in the set. And in 1985, Baba and Shosh posed this one problem. Given G, finite, they gave an example, the alternating group of even permutation. What is the largest product free subset?
What does it mean, AN?
The alternating group. The group of even permutations.
Permutations.
Even permutations. Yeah, so what they conjectured, that was in 1985, was that for every finite group, there exists a subset of G size at least C, and G was C is an absolute constant, not depending on the group. Such that A is product free.
Absolute means it does not depend on G.
Yeah. Somehow there is a very famous open problem about subsets of the integer. There is a result saying that every set contains a subset of size A over 3 that's sum free, and getting from A over 3 to A over 3 plus omega of 1, that's an open problem, and it's related somehow to the Littlewood conjecture. I guess that was their motivation. But actually, 2 years later, Kindler conjectured contradicting conjectures, so conjectures without their own. So, okay, so we gave the following construction. So suppose that you have a group G that acts on set X. And suppose that you have an element X in X and a set I contained in X. Then you get the following construction. So you can take all the elements such that G of X is in I, and G of I is contained in the complement. And this conjecture was that the largest product free subset of An is of the form Kxi. Kxi, where we look at the action of An on the numbers 1 up to 1. So basically, the set of permutation in An or alternating group such that sigma of 1 is in 2 up to m, and sigma of 2 up to m is disjoint from 2 up to m. So you conjecture that the construction is essentially optimal, and such a construction has size at most 1 over root n.
No, well, frankly, the last line is not very visible on this.
Okay. Yeah, I can. Okay, so So the largest product-free subset is of the form kxi for, let's say, x being the set 1 up to 1. So the alternative group acts on the set 1 up to 1, and then you can take the set of elements and send one set and this set to a complement. And you'll get a product-free set, because if you multiply two elements from two permutations, the product. Okay, maybe I should just write why it's product-free. So suppose that sigma of x is in I, right? And so suppose that sigma and tau are in kxi, then sigma of x is in I, and tau of the set I is contained in the complement of I. So this means that tau of sigma of x is not in I. So tau sigma is not in kxi. Okay. So this is a construction of a product-free set. And the optimal way to choose the set I is take it to be of size root n because of the Berti paradox. The probability that the set two subsets of size root n is disjoint is a constant. If you start to take it take a set larger than that, the probability that disjoint starts to become much smaller. And I'm telling you about this problem because it turns out that the methods that are helpful for solving KKL are relevant for tackling these type of questions. Are there any questions? So basically we have two conjectures. One conjecture says that there always exists a set of constant density, and then there is a contradicting conjecture that says that the largest one is actually of this form. And Gowers showed that the first conjecture is false. Okay, so Gowers showed that every product-free subset of AM has size at most n minus 1 to 1/3 times the size of the group. And then this was improved by Eberhard.
So then what is n?
It's the alternative group on n element. It was improved by Eberhard and then completely solved. So with Peter Keevash, And the Minzer we proved that the Lias conjecture is true. So actually, the largest product-free subset of AN is of this form. It's exactly this form.
Something funny with the Gauer's bound, which is this negative. It's n-1 to what power?
1/3.
But
N minus 1 to the minus 1. Okay, cool. But so this result also used hypercontractivity, but I'm going to talk about a setting where these things are simpler, which is the setting of compact groups. So, suppose that we have a compact group. Then there exists a half probability method. So it's a measure that satisfies it's both left invariant and right invariant in the case of compact groups. So mu of GA is equal to mu of AG for every measure of LA. And G and G. So instead of talking about the largest inside, we can talk about the largest Haar measure of the product free set. And what is the largest product-free set? So in the special unitary group. So SUN is a set of matrices such that are unitary and also the determinant of A is 1. Okay, here maybe I should write measure of a set in SUN. And here you can construct a set similar to the Kedlai construction. You have the action of SUN on the sphere. The complex sphere. And then you can take all the elements and the north pole close to the south pole. So you can take A to be the set of elements. Let's say sigma of E1 is close to minus E1. And because unitary matrices preserve distances, if you send E1 close to minus E1, so if sigma of E1 is close to minus E1, and tau of E1 close to minus E1, then you get that the product is close to itself. And the measure of A is exponentially small in M. Because this is a ball in space of dimension 2n minus 1. So mu of A is into the Cn. And Gauss conjectured that this is optimum.
It's minus again.
Minus, yeah. Okay, so this conjecture by Gauss is still open. So if A is product free, then the measure of A is the smallest e to the minus Cn for an absolute constant. Independently, physicists asked a similar question because they were interested in separating quantum communication protocol with classical one. So they had this quantum communication protocol that was very quick, and they wanted to show that every classical algorithm, it will take much more time to do the same communication task. And then they conjectured a qualitatively stronger conjecture, which is quantitatively weaker. That's conjecture of physicists. So suppose that suppose that they have this subset of S2n. And you have three sets of measure at least e to the minus Cn 1 over 3. So the conjecture is that for arbitrary set, if I choose randomly A in A and B in B, then the product AB is already uniformly distributed in SUN, and it's so much uniformly distributed that the probability that AB is in the set C is very close to the measure. So it's in between mu of C times 0.9, let's say, to mu of C times 1.1. And this conjecture, so if A is product free, so if the conjecture is true, then you take A to be product free, then this probability, and you take A, B, and C to be equal to A, this probability becomes 0. But then, so this would imply that this set must be small. So let's call it the product mixing conjecture. And actually, and if it's true, this would be sharp because there is a similar example to this ball that shows you can improve. So basically it tells you that if you have 3 sets that can be quite tiny, then the following counterintuitive thing holds. If you take 2 random elements from these tiny sets, the product already must be uniformly distributed in SUN, and this thing is equivalent to somehow mixing times 3 in L infinity.
Well, L equals 1. Probably it's trivial. Okay.
Okay, but if the product mixing is true, it would imply that product free sets in SUN are small, so they must have measure e to the minus Cn to the 1/3. And what Gauss knew, something much weaker. So Gauss proved that product free sets subset of SUN, proved it using the representation theory. As a measure of most n to the minus 1/3. what we proved. The product mixing conjecture